questions? Okay. All right. So we'll now look at the last of the three. So all paths shortest path. Now, the first two algorithms actually are said to follow a greedy strategy. A greedy strategy means you try to kind of look at the estimated path weight for your neighbors and see if you can use one of your neighbors to um, reduce the path weight. So for to find the estimated path weight for or reduce estimated path weight for D, you looked at the estimated path weight to reach one of the all the neighbors, and just use the path weight to the neighbor plus the edge weight and pick the neighbor with the lower estimated path weight to reach D. So you just look at greedy with just the incoming neighbors. You do not look at the entire graph to decide it. Similarly, in Dijkstra, in each iteration, you pick the vertex with the smaller value weight among the estimated path weights and say you have optimized the vertex. So that's also a greedy strategy. So both the greedy strategies give you the optimal solution. You are finding the shortest path weight. Now, to do the all paths shortest path, we are going to apply a dynamic programming approach. Okay. So let us look at kind of like a motivation example or scenario to see why we need dynamic programming. Okay, so the general principle of this algorithm is this. You want to find the shortest path between any two vertices. Now, it requires us to label the vertices. As part of the operating principle, we are required to label the vertices from 1 to n, and that means you are going to go through n iterations if you have n vertices, and the vertices are required to be labeled from 1 to n. Okay. Now, so the operating principle is this: in the kth iteration, we are going to consider vertices from 1 through k as the possible intermediate vertices for the shortest path between any two vertices. So what does it mean? So let us say in iteration 3, between any two vertices I and j, the shortest path between the two vertices I and j could have either just one. So it could be I1j is the shortest path, or I2j is a possible shortest path, or I3j, or I12j, or I21j, I13j, all possible combinations of vertices 1, 2 and 3. And we can also use this for directed graphs. So that's why I say we can have I12j or I21j, both are different paths. So we are going to consider, if you are going to do a brute force approach, we have to consider all such possible paths between I and j and find their corresponding path weight and pick the minimum among them. Now again, that is the shortest path weight involving only 1, 2 and 3 as the possible intermediate vertices. So that means in the kth iteration, we have to consider all possible combinations of vertices 1 through up to k. Okay, so like for example, in second iteration, we can have only vertices 1 and 2 as a possible intermediate vertices. So the number of combinations you have to consider for any two vertices I and j could be either, again, I to j could be a shortest path, or that means when you say I to j could be a shortest path, you are not considering any intermediate vertex, because one combination of 1 and 2 is without considering 1 and 2 itself. It's an empty set as an no intermediate vertex. Or I1j, or I2j, or I12j, or I21j. So these are the different combinations that we have to consider for the second iteration. Okay, because iteration 2, the iteration number corresponds to the maximum number of vertices from 1 through that many vertices. So in iteration 2, we can consider 1 and 2 as the intermediate vertices. In iteration 3, we can consider 1, 2 and 3 as the intermediate vertices. So in iteration k, we can consider 1 through up to k as the intermediate vertices. So if we were to do a brute force approach to do this problem, that's going to be very time consuming. So that's why we go through a dynamic programming approach to do this. So that means, so let me first explain the general principle. It may not be 100% clear, but once we start doing the examples, it will be very clear. Okay, so the general principle of this dynamic programming approach for this algorithm is this. So in order to consider vertices 1 through k, that means in order to do the kth iteration, we should have done up to k minus 1 iterations. That means we would have found the shortest path, again the estimated shortest path between say two vertices I and j, involving only vertices 1 through up to k minus 1, because that's what we could do in the k minus 1 iteration. Again, like I enumerated all the possible shortest path, if you were to find the shortest path from between I and j, or from I to j, involving vertices 1, 2 and 3, you need not always involve all the 3 vertices. So involving 1, 2 and 3, it could be like I1 to j itself is the shortest path by considering vertices 1, 2 and 3. So all we have to realize that all the 3 vertices need not be part of a shortest path. So that means in the k minus 1th iteration, all the k minus 1 vertices need not be part of that shortest path between or from I to j. It could be some subset, some combination, some possible subset of the vertices from 1 through k minus 1 could be part of this estimated shortest path between from I to j, the k minus 1th iteration. So that's what we are having at the end of the k minus 1th iteration, the estimated shortest path between any two vertices. So that means between say from I to k, we'll look at it as a directed graph. So I'll say from I to k, from I to j, from k to j. What we have found is the estimated shortest paths involving vertices only 1 through k minus 1. So now we are going to the kth iteration. So it's similar to some of the dynamic programming problem that we went through earlier. We have to decide whether to include the kth vertex as an intermediate vertex or not. Okay, so that's the thing we are going to decide in the kth iteration. So in the kth iteration, we are going to decide whether to include vertex k as an intermediate vertex on a shortest path from any vertex I to a vertex j. So at the end of the k minus 1th iteration, we know some weight for this shortest path, estimated shortest path from I to j. So let us indicate that as d of I comma j at the end of the k minus 1th iteration. So that is the distance or the estimated shortest path weight from I to j at the end of the k minus 1th iteration. Similarly, at the end of the k minus 1th iteration, we have some estimated shortest path weight from I to k, that's indicated as d of I comma k at the end of the k minus 1th iteration. Now similarly, we can say at the end of the k minus 1th iteration, the estimated shortest path weight from k to j is indicated as d k comma j, or with the prefix superscript k minus 1. Okay, so superscript indicates the iteration number, so that's k minus 1th iteration. So now what we are going to do is whether we can reduce the estimated shortest path weight from I to j by involving k as an intermediate vertex. So let me see if I have an example here. Okay, well, let me use some numbers here right away. Okay. So let us say this is the distance from I to j that we estimated for d I comma j at the end of k minus 1 is 100. And let us say from I to k, the distance we estimated, the shortest path weight is say some 20. And from k to j, let us say the shortest path weight we estimated is 40. So it is 20, 40 and then 100 from I to j here. So that means we could really go from I to k using a path weight of 20 and from k to j using a path weight of 40. So 20 plus 40 is 60, less than what we currently know from I to j of path weight 100, right? So that means instead of going from I to j on this brown colored path, we can really go from I to j using k as an intermediate vertex. So we'll first go from I to k and then go from k to j, right? So we can choose that path if what? The distance from I to k, the k minus 1 titration, plus the distance from k to j, the end of the k minus 1 titration, is still going to be less than, so the blue one. So you will prefer the blue one if the distance that we go from, that we know from I to j, is greater than the distance from I to k plus the distance from k to j. As I said, if it is 100 from I to j on this brown colored path, it is greater than I to k is 20, k to j is 40. So 100 greater than 20 plus 40. In that case, we can say the distance from I to j at the end of the kth iteration will be the blue colored path, from distance from I to k plus the distance from k to j, right? On the other hand, if it is something, say 50 as the distance from I to j, and this is 20 and 40 still, so 50 from I to j at the end of the k minus 1th iteration is not greater than 20 plus 40. So that means we will stay with what we know currently, right? So that means we are not going to involve k as the intermediate vertex for the kth iteration. So even though we say we are going to consider vertices 1 to k as a possible intermediate vertices for the kth iteration, depending on the path weights we end up with, we are not really going to go through k. So the estimated path weight at the end of the kth iteration from I to j is going to be the same as the estimated path weight from I to j at the end of the k minus 1th iteration. Because, like as I said, 50, the estimated path weight we found at the end of the k minus 1th iteration, is not greater than 20 plus 40. So we stay with what we know currently. So we can reduce only if possible. So if it is 100, it is greater than 20 plus 40, then we go through k and say the estimated path weight from I to j at the end of the kth iteration is the estimated path weight from I to k at the end of the k minus 1th iteration plus the estimated path weight from k to j at the end of the k minus 1th iteration. So that's how we keep reducing the estimated path weight. We always take the minimum of what we know currently and what we can achieve by going through that vertex k in the kth iteration. Okay. Now when we do that, we have to also keep track of the predecessor. So if this vertex was the predecessor currently we know from I to j at the end of the k minus 1th iteration, if you are staying with that path even at the end of the kth iteration, then the same predecessor will be used. So that's what I indicate here. The predecessor at the end of the kth iteration from I to j is the same as the predecessor from I to j at the end of the k minus 1th iteration if you use the red one. That means this is not brown, it's actually red. If you use the same path that we know from the k minus 1th iteration, so if you're not changing the path. On the other hand, if you are really going to go through k and reach j to go from I to j, the predecessor at the end of the kth iteration is going to be like what? So if you go through k, you have to go on this path from I to k and then on this path from k to j. So the predecessor from I to j is going to be this vertex on this path from k to j. So this vertex on the path from k to j, where I have placed the cursor, is also the predecessor of the path from k to j, because this is like a subpath from k to j. So this is the predecessor from k to j in the k minus 1th iteration, and that vertex is also now the predecessor from I to j at the end of the kth iteration, because to go from I to j we have to go to k first and then take this path from k to j. So the vertex that was the predecessor from k to j at the end of the k minus 1th iteration is also now the predecessor to go from I to j at the end of the kth iteration. It's the same thing. So that's what I indicate here. Pi, so pi to indicate the predecessor. So pi kj at the end of the k minus 1 titration is going to be the predecessor for pi ij at the end of the k titration. So this is the predecessor now to go from I to j at the end of the k titration if we are really going to go through k. If you are not going to go through k, you are just using the same path that we had at the k minus 1 titration, that then same predecessor is used as the predecessor at the end of the k titration. Pi ij at the end of the k titration is same as pi ij at the end of the k minus 1 iteration if you're going to stay the same path. If we're going to change path and go through k, then we have to change the predecessor also, corresponding to what is the predecessor on the second path, subpath from k to j. So that's the working principle, and once we go through the example, this will be clear. Okay, so in order to do the examples, let me tell you again a way to do the math to keep it simple. So again, what we are going to update is the entry for I comma j, the pair I comma j. So let us say I want to update this cell I comma j, the value here. So since it's all pairs, shortest path, you need a matrix between any two pairs of vertices. So looking at a cell I comma j to find the shortest path from I to j. So you want to decide whether to update the value in that cell I comma j, which is the distance that you estimated for I comma j at the end of the k minus 1 titration. So now we are doing the k titration and we are trying to see whether we can reduce this I comma j, the distance, further. So if you look at the recursion here for dynamic programming that we have, we are going to, if we are really going through vertex k, it is distance from I to k at the end of the k minus 1 titration plus the distance from k to j at the end of the k minus 1 titration. So I to k plus k to j. So where should these entries be in this matrix? So again, so distance from I to k is going to be this entry, and distance from k to j is going to be this entry, okay, because we're looking at I as the row index and j here is the column index. So this is cell I comma j. So I comma k will be some entry here, k comma j is some entry here. So we are going to add these two. So this entry will give you the distance from I to k, this entry will give you the distance from k to j. So if the sum of these two entries is going to be less than what we currently have for I comma j, then we are going to update I comma j. So how to do this? In the k titration, okay, we are going to consider vertex k as a possible intermediate vertex. So as we go to examples, this is what we are going to do. We are going to highlight the kth column and the kth row to make the calculations easier, and update the other entries in the table, because the kth iteration we are going to consider vertex k. So this row and column are not going to change in the kth iteration, only the other entries are going to change. So if I comma j is a cell here that doesn't fall in this row and column, then this is what we are going to do. We are going to compare the value currently we have for the cell I comma j with the sum of the values for the cells I comma k plus k comma j. If the sum of these two distances is going to be less than what we know currently for I comma j, then we are going to update this entry I comma j to that sum, and that corresponds to this the blue thing. So I comma k plus k comma j, the sum of the two distances. If the distance that we know currently from I to j is greater than the sum of the distance from I to k plus some k to j. Now when we do that, I said we have to also update the predecessor to what? The predecessor that we know currently from k to j, and that's what we'll be doing in the predecessor matrix. So we'll be maintaining two matrices as we go through the examples. One matrix to keep track of the distances, the other matrix to keep track of the predecessors. So the predecessor to reach now from I to j is going to be the same as the predecessor that we know from k to j. So that means if you want to update the predecessor for I to j in the kth iteration, consider the kth row and the cell k comma j. So whatever is the entry here in the cell k comma j, make that as the entry here for the cell I comma j. So that's the predecessor, because that's what we did here. The predecessor for from I to j is same as the predecessor from k to j, this particular vertex. Whatever is the predecessor from k to j is same as the predecessor from I to j. So that's what this matrix entries indicate. Okay. So this is the working principle of this. So the algorithm is called Floyd Warshall, or the all pass shortest path algorithm, and we'll make use of this and do some examples. Okay. So let me stop so for a minute to record this video.